Hello, everyone, and I have great honor to introduce our speaker for today's webinar in March, Claire Monteleoni. So I'll say just a few words, and then Ignacio will take the lead. So Claire is well known, is one of the very first people who tried to bridge the two communities, particularly computer science and machine learning, with climate and atmospheric sciences. And she has founded Climate Informatics Workshop. And this is now a big thing, and it's the community of its own. And Claire holds a position at University of Colorado Boulder in computer science. And since January, she is also Choose France Chair in Artificial Intelligence at INRIA Paris. Okay, and it's absolutely amazing that Claire has agreed to give a talk and fit into her schedule. And Ignacio will provide more details. It's Ignacio, the floor is yours.
Thank you. Thank you, Julia. This session consists of 40 to 45 minutes presentation and 10 to 15 minutes for questions and answers. We suggest attendees to ask questions at the end of the presentation. We are so glad, as Julia mentioned, to present our today's speaker in this TAIES webinar series on data science for environmental sciences. Claire Monteleoni, thank you so much. Julia already mentioned a good part of your biography. That's great. I just wanna add that the International Conference on Climate Informatics that actually you co-founded, it's turning to 12 years old this year and has attracted climate scientists and data scientists from over 20 countries and 30 US states. And actually, it's awesome having you here because, you bring all the experience, not only on research, but also on leadership, since you are currently serving as on the NSF Advisory Committee for Environmental Research and Education. So, dear Claire, thank you so much for accepting our invitation and making time out of your really, really busy schedule, and welcome.
Thank you. Thanks everyone for being here and also for the time adjustment. I really appreciate it so that I could join from Europe. So this photo here is from Colorado this past summer. And we've got beautiful nature, forest, river, and then we have wildlife. We've got some deer, but then we also have some infrastructure, a bridge, and also even power lines. So we're going to have to figure out how to make this all work and all live together. Now, on a much sadder note, also from where I've been living up until recently in Boulder County, is an example that I want to highlight for a real frontier, which is about cascading extreme events when multiple anomalous things happen and together they cause outsized impacts. So in Boulder in the fall of 2021, it was anomalously dry. We had snow drought, so we didn't have enough snow in the mountains, and in general, the vegetation was quite dry. And then we had a very strong wind event. It was actually preceding a snowstorm, but winds up to 80 to 100 miles per hour were observed. And so then all it took was a single ignition, and there was this, we would call it a wildfire, but this was not out in the wilds. This was just leveling suburban neighborhoods. It was really more of a grass fire, and it moved like a storm. So it jumped over our main highway in multiple places, and over 1,000 homes were leveled to the ground, just in the course of that one day. So that's where we had, drought combining with an anomalously high wind event. There are other sorts of cascading hazards, such as in Central Coast, California in 2018. So we're talking California, of course, there had been years of drought. Then there's a wildfire in a high forested region. And as that burn scar is nearing containment, there's an extreme rainfall event. And this produced a debris flow, is the technical term, but you should really be more scared of it than it sounds. So think of boulders falling through your living room. This was actually a highly fatal event, and you can see here the mud and the debris flooding into homes. So having the drought followed by the fire and followed by the extreme rain can cause an outsized impact of that sort of debris flow or landslide. And more generally, I'm bringing up these extreme events as more generally a motivation for why to take your tools that you have, your analytical tools, and study climate change. So we study climate informatics due to the threat of climate change and extreme events and their impacts on communities and ecosystems. And climate informatics is based on the vision that machine learning can shed light on and help address climate change. And these sorts of ideas are starting to be picked up even in public and economic forums such as the World Economic Forum, who said, noticing that AI is advancing some of our other private sector domains, what can AI do to help with our environment and addressing climate change? And thanks to both of you for mentioning climate informatics. I'm not going to give a whole history. I will mention it in case anyone wants to quickly fly over to the UK, that the conference is coming up this year with a hackathon. And actually, they're doing a reproducibility hackathon for papers in this space. But just a few key things to note. I think one of them is that when you have a transdisciplinary domain where you're trying to get lots of people to collaborate together, it's nice to create events, social events, places to go hike and drink beer. That's worked in Colorado for a while, but also publication venues. And so we started with archival proceedings at our conference, and that's great for computer scientists. We like to publish in conferences, but pretty much no other field does primarily focus on conferences. And so it became important to launch a journal in this general space. And actually, I noticed that at least one of our editors of environmental data science is on this call. The other thing we noticed, in addition to creating events and publication venues, is the idea of these hackathons, where really, whether it's virtual, as we had to do during COVID, or in the same room, getting together smaller groups for individual collaborations, often students, where one person has training in Python, another person has taken a machine learning course, and they probably also have Python training. But then we also have people that are scientific domain experts in the problem at hand. And those have led to individual collaborations. These individual collaborations have led to articles, grants, even full funded centers. So that's really exciting. And yes, an experience in this in building a transdisciplinary research community. So I wanted to just give a survey of thrusts that I'm interested in, both that I've done in past work and more recent work, and then ongoing work, and sort of the scope I see for where machine learning can make an impact in confronting climate change and working towards environmental sustainability. We started with those cascading hazards, and I view that as even beyond frontier, because at the moment we can maybe use AI to work on forecasting any particular hazard. But really, I want to take that as a goal, because we needed solutions yesterday. You know, homes and lives are being destroyed, and these cascading hazards have outsized impacts. And that falls under my middle bullet, which I've done in blue just to alternate colors. And there's a lot of words in these bullets, but let's think of it more as that middle one as AI for climate adaptation. Wherever the source of these extreme weather events are, they are already happening. Let us get better warning systems, and warning systems that really also value climate equity and climate justice. The first bullet being really where my history has been, which is AI for climate science, about better understanding and predicting longer term climates. And then finally, towards mitigation, the third bullet is really about using machine learning to speed up the green transition. So this is going to serve as the outline of my talk. I'm going to basically describe a little bit in each and maybe do one deeper dive vignette. If you came because you're really more of a methods person and you're not yet convinced that you want to work on climate change, I will just briefly point out that it's possible to work at the sweet spot. So actually, by engaging with domain experts that have these impactful problems and large, interesting data sets, we might come up with things that are open in machine learning. And so this is going to be on the menu. I'll try to point out when they pop up, and then I'll come back to it in the conclusion. Machine learning for climate science often involves interfacing with climate modelers, and climate modelers have developed climate models, which are large physics-based software simulations of climate. Well, what does that mean? So there's 4 big systems: the atmosphere, ocean, processes involving land, and processes involving ice, the cryosphere. And these 4 very large systems can be broken down into smaller individual components, which are governed by laws of physics in terms of energy transfers, things like heat advection. And so each of those individual components, we'll call them, can be written down, some of them as a closed form partial differential equation that models that exchange, and some of them have to really be more approximated to compute at scale. And then you have questions of, well, how does the atmosphere couple or interact with the ocean, which is a very hard task. So even in terms of, so it's hard due to the large differences in scales. So on the spatial scale, if you really want to simulate a cloud, you should be looking at an individual aerosol particle and simulating, a water droplet condensing around it. Now that level of fine spatial detail is not simulated in the global models. They're going to have resolutions on the hundreds of meters. Meanwhile, when we're coupling between the atmosphere and the ocean, the ocean circulates on order of hundreds of years, and the atmosphere circulates on the order of weeks. So again, we have massive numerical differences that come to a head when we do the coupling. So all this to say that climate models from the different teams across the world who contribute simulated projections of future climates have had to, engineer and design ways to simulate the science that derives from the physical first principles, but the teams have done it differently. And so the idea we had was to treat these models as just black box predictors, where you have lots of predictors saying different things going into the future. And then how can we use machine learning to sort of adaptively combine them? So I'm going to do a vignette on that. This is the first bullet. But I did also want to mention that when we think about climate change also at multi-year scales, not maybe all the way out to 30 years, but just a year or two in advance, we have to think about the drivers of what we often observe in weather, the climate modes of variability. So the one that you're probably familiar with is that you've seen, you've heard about El Nino events and La Nina events, and that process is called the El Nino Southern Oscillation, which is already hard to predict, even if there were no climate change, because it doesn't have a set period. It sometimes can repeat in as few as 2 years, sometimes up to 9 years. But then it's also understood that this general warming trend and other changes that we're seeing in the climate can be pushing or changing how this oscillation works. So there are other domains of ML. I'm not going to talk just strictly about deep learning, such as causal inference, that can be helpful in seeing what the indicators or future indices might need to be for something like ENSO, so that we can reason about how climate change is changing it. I also want to briefly mention this highly ambitious project that we have that's funded by NASA, where we're working with the NASA Sea Surface Topography team at very precise satellite measurements of sea surface height that are geographically explicit, but then trying to use the modeled data from these big climate models to help us project out into the future, because the altimetry data is only 30 years of the past 30 years. So how do we predict sea level trends way into the future using those two sources of data? So the vignette for this topic, I'll say AI or machine learning for climate science, is about this line of work we did, also not with deep learning, with a technique called online learning, where we had the predictions from multiple models, but we have non-stationarity, right? So the observations are changing with time, and so this means that model performance is going to change over time. And we applied algorithms for online learning from a bunch of expert predictors typically used in the stock market for learning under non-stationarity. And then due to the application area, we thought, well, actually, we have non-stationarity also over space. And so there are sort of various ways you can go about addressing it, but my graduated PhD student, Scott McQuaid, came up with an interesting way of doing this that is still very lightweight. It's not running a whole conditional random field, which could sort of blow up. It's really more along the lines of distributed online learning. And then, much later, talking to some theorists in online learning, the guy that wrote the book on online learning, Niccolò Cesabianchi, we realized that actually, we had proposed algorithms in a framework that was new for ML, and we're able to spur on some theorists to then contribute to algorithmic learning theory on how would you evaluate such distributed online learning algorithms. Now, this turns out this can even be useful in finance. You might actually want to exploit similarity in time of predictions at different temporal leads. And so you might need to exploit neighborhood structure, not only in space, but also in time. So again, quick vignette, happy to talk more during the Q&A about any of these thrusts. The second main axis is what machine learning can do around climate adaptation. And this is where I'm sticking extreme events because, ready or not, these are already happening. And how can communities better adapt and prepare? So on the left is a figure of a paper that was led by Sophie Gifford-Rosen, who did a postdoc in my group, where given data of storm tracks that is available from this great NOAA storm track database, she registered other relevant fields other than just the lat-long location of the storm center around that lat-long location of the storm center, to create things that look a lot like image data, but it's just real valued fields such as wind and pressure at multiple geopotential heights. And then this then allowed us to do a CNN-based solution that fused multiple data types, learned the weights to make that fusion most effective at doing this supervised learning task of predicting where the cyclone will be 6 to 24 hours in advance, which ended up being competitive with state of art. And so we sort of recommend that these could be used as a decision aid in addition to the other tools in the toolbox of the humans who have to sort of make sense of what all the different models are predicting. So the vignette that I wanted to focus on today is going to be about avalanche detection. So the other things just to kind of note here on this slide is, some of our work around extremes can be highly societally impactful. So, Indian summer monsoon affects the GDP of that entire subcontinent. And my former postdoc, Mumita Saha, worked with the Indian Meteorological Department to actually embed some AI techniques in how to forecast some of the extremes that we can see that drastically affect agriculture in the region from this very hard to predict problem. And then an older work that we did was a very interesting proof of concept that unsupervised learning has value in these applied domains where typically things had not been defined in a probabilistic way. So if you talked about an extreme temperature reading, that would literally mean exceeding some threshold. Or if you wanted to talk about an extreme event, it would be hard to talk about it in a multivariate way. You just had these kind of blocky thresholds on each variable. What if we could have a multivariate probability distribution as the signature of each kind of extreme event? And so using a Bayesian sort of hierarchical clustering technique, latent Dirichlet allocation, my former student Chung Tong did this for climate topics. So now we can detect multiple kind of extremes other than, which is different from how things had been done in the past, from multiple variables, and have our representations of the signatures of these extreme events be soft and probabilistic. Okay, so this avalanche case study was work with Météo France, which is like NOAA for France. And they had a ground truth survey in the Alps where they would go into avalanche corridors, places where avalanches might fall in a snowy time, and check where avalanche deposits were located by having human trekkers on the ground go and look for the texture of the snow being different with or without the avalanche deposit. Now, that's really dangerous, and they sent a limited number of people to do this a limited number of times, and so they had this one sort of gold ground truth data set. But then we can kind of think of our remote sensing data as more ubiquitous. So using synthetic aperture radar from these Sentinel products, we could really have unlabeled data for the region as well, but we don't have any in-between product. You can imagine a product that is the SAR data that has been manually segmented by an expert of where avalanches fell. They said this was quite hard. It was very hard for a human eye to distinguish, although they were going to train them. But at the time, we just had unlabeled SAR imagery and then a limited ground truth survey. Putting machine learning jargon on this, or phrasing the challenges for ML, if we're looking for avalanche deposits, those are rare. So we're going to have class imbalance. Say we treat avalanche deposit in a patch of an image as a positive example. We're going to have much more negative examples than positive examples. But that is coupled with only having a small and finite amount of labeled data. So just to approach anomaly detection, let's set up a pipeline that is pretty traditional, which is that, okay, acknowledge that if you're trying to predict if you're trying to estimate something that is rare, you can term that as anomaly detection. And one thing that had been emerging in the literature was to learn a model of the nominal class. So learn a model of image patches that don't have avalanches in them. And we were using a VAE, which I'll talk about on the next slide. And then when a new image is fed to the model, if it's similar to the data that the model was trained on, then the output image will be very close to the input image. But if it's different, there'll be a larger reconstruction error, which compares the output image to the input image. So this is a pipeline that can be done for anomaly detection, and that kind of addresses our first bullet on the previous slide of class imbalance. But it doesn't address the second bullet about there being only a limited amount of training data. In particular, there's this hidden step 1.5 where I would have to produce negative examples. How do I do that? Well, I actually have to look at my ground truth survey, compare it to my SAR images and find images, image patches that are negative examples. And so in some sense, I am already touching the label data, and that means I've wasted it and I can't use it later in my training or validation. Now, the training itself doesn't need label data, so that's fine. But you do have a hyperparameter that you need to tune, which is the threshold above which you'll say that you have an anomaly, the threshold on the reconstruction error. Hyperparameters do have to be tuned with labeled data. And so our twist is to replace step 2 with training a model on unlabeled image patches. So there's no labeled data that was harmed in the process of doing step 2 now, because we just sample image patches. We don't know what they have in them, and then we train a model using that. And actually this then works nicely in the pipeline. A bit unintuitive, but we'll go through why. And first, I'm just going to briefly go through what is an autoencoder, which is a very stupid machine, because once trained, it's basically like an identity function, but worse. It's like a noisy version of the identity function. Here is like a pixelized version of somebody drawing a digit, and we just have a grayscale image. And then we feed it to this trained machine, and we get something quite similar to it, but more fuzzy. So nobody needs that machine. It's not really good for this task, but this task is called a pretext task, because while trying to get the output similar to the input and training these weights, doing gradient descent on the loss, which is the reconstruction error, typically with maybe some regularization. What do we get? Well, if we've sent the data through a bottleneck, meaning it's lower dimensional than our input, then hopefully this bottleneck layer, after training on many such images, will encode the images in some way, i.e. project them into a different space, usually a lower dimensional space. And we like that. We like compact representations because we need efficiency, and we want to, glean some latent patterns out of very high dimensional data. So that's what is typically meant by an autoencoder. And often in these sorts of applications, you will be going through a bottleneck layer that's called a dense autoencoder. It is possible to actually go through a layer that is higher dimensional than your input and output. And the point of doing that is that you might want to have very, very sparse representations that are separated. This is often the case in like cognitive science. It's been shown in other species that for sensory recognition, sometimes there's a projection to a higher dimensional space so that items can be quite different. But I think for most applications in climate, you'll generally want to go to a low dimensional space. We're going to call that your latent representation. And then you might want actually a probability distribution over that latent space. And the first one that really gained traction was using a Gaussian. And that's how variational autoencoder was originally defined. Since then, there have been further techniques such as normalizing flows, I'll mention towards the end, where you don't have to have a Gaussian distribution on your latent space. It could be something else. Okay, so ending that detour, for those that already know VAE, you can pay attention again. But so the pipeline that we were talking about, there was the straw man version, which is how it was done in the literature, which is that there's a step where you label your images by using the ground truth survey, and then only give negative examples into this into training this architecture, this variational autoencoder. And the training is gradient descent on this reconstruction error, regularized reconstruction error of how close your reconstructed image is to the input image, forcing it to become closer and closer. And that's how you tune all of these parameters, including those of the Gaussian. Okay, but then we said, well, that's a straw man approach, and we're going to actually skip this step and replace it with still training of VAE, but just on image patches from SAR that we haven't bothered to label. Okay, so you do one or the other. If you're doing the straw man approach, which we'll compare to, versus our approach, you will do one or the other. But in either step, in either stage, you do have to do a step of hyperparameter tuning. Why is that? Well, ultimately, anomaly detection has to output a class, anomaly or not, right? Avalanche or not. And so we have this wrapper around the trained autoencoder that's going to rely on a threshold. It's thresholding this difference between the input and the output. And you train a hyperparameter on labeled data, which means we've looked at the ground truth survey. We know whether there was an avalanche. So there's no avalanche in these patches and there was in these. And so we'll toggle this threshold until we get a nice matching of labels with respect to the decisions that we would make with this threshold, hyperparameter tuning. And then once tuned, how does it work? Given unlabeled images, I will feed them through the trained model, compute the reconstruction error, compare it to the threshold, and then that gives me my label. So as I foreshadowed, we actually got more of a performance improvement by training on unlabeled data than on negative examples only. But first, so there's the baseline method that our Météo France collaborator had used was some engineered way of thresholding the SAR product. This is a very tough task that did not, do that well. And then also, the first year we worked on this, we tried supervised learning, but we had to artificially balance our classes, which meant we were training on not a whole lot of data and did actually even worse than the non-learning method. And then our first technique where the VAE requires some supervision even to learn, because we had to find the negative image patches, did get a lift above the previous approaches somewhat, but the bigger lift was when we trained just on those unlabeled image patches. And this sounds counterintuitive at first, because now there might be some avalanche patches in our training data. But the key thing to remember is that after each of these are learned, they each independently get their hyperparameter tuned. In fact, to create a table in any machine learning paper, all methods with hyperparameters independently get their hyperparameters tuned to be best for each method on the same fixed, held out, labeled training data set. So it's because of that we're going to probably have a completely different threshold in the two different cases, but the threshold is tuned to optimize each of those algorithms. And then the more kind of philosophical reason is that we conjecture is that because you're training on, first off, a larger data set, since you aren't limited to not have the positive examples, but also more diversity in the feature space, you've sort of seen more of the range of the features, which generally helps to reduce overfitting and improve generalization. So this was hopefully a message to machine learners or other people applying these techniques in their applications, which is that if you only have a little bit of unlabeled data, just use it for hyperparameter tuning and lean on unsupervised learning as much as you can. The other aspect that I wanted to just briefly mention is how this relates to impacts and equity. So often you have data-rich regions and data-poor regions, even within a single country, but that's certainly true about, our global north versus our global south. And so if we have a way to take ubiquitous data, remote sensed products, and learn ML models trained on small ground truth data sets, then those ML models can sort of like virtually create fake data in the data poor regions, or for example, replace the sensor, which in this case was human trekkers in a dangerous region. The last thing I wanted to talk about in terms of directions that this is really at this point more some ongoing and future work is how machine learning can help speed up our transition to a greener, ideally, industry and economy. And where we've started now is in the transition to renewable energies. So back in Colorado, we have collaborators at the National Renewable Energy Lab. And to get a grid operator that's only constrained by capitalism to choose to use renewables, you have to make it cost effective. But if it's something like wind or solar that can sometimes generate power and sometimes not, you want better predictability. So even just a slight lift in predicting when you're going to have the solar output or wind output can reduce cost and help incentivize these sorts of sources to be incorporated into the grid. And we found it actually was very hard to do better at very short time scales, at least for solar irradiance forecasting. So for minutes up to an hour, generally it was better to just assume persistence, which is, okay, the irradiance that I have right now will persist for the next few minutes to an hour. That will generally do better than very fancy ML. But we did have scale at around week ahead forecasting, which is important because like numerical weather prediction models are not updated often enough that they could give a good, like a skillful week ahead forecast at any time of the week. And so we were able to have better skill than they did. And then I'll briefly mention that one idea in terms of going from data rich areas to data poor areas is that you can, so often there's so many problems that can be phrased as downscaling, which in the computer vision community might be phrased as super resolution. So basically climate models give us all these wonderful projections into the future, and say like solar irradiance fields would be very useful for renewable energy planning, but they're at a very coarse spatial scale from the climate models. So we'd like to do downscaling, and we have products that were derived from observations, such as reanalysis products, that are at fine scales. So you could do supervised learning where you have this fine scaled product, but we also showed that you could do unsupervised learning for downscaling. And then you can sort of check that these are well calibrated in your data rich regions. And then you could take the unsupervised models or even supervised models that you might want to fine tune to your data poor regions. So this is not only helping to forecast into the future, because the future is data poor, but also into countries, say in the global South. So we recently are wrapping up a project that was doing this in certain parts of India. Just a brief note on this general unsupervised method for downscaling, and this was led by Brian Gronke, who did his master's in machine learning and computer science at CU Boulder, and is now at the Alfred Wegener Institute in Potsdam in a climate PhD program. So the idea is, unlike the statistical downscaling literature that we were aware of, where you could learn to downscale given paired maps of a data field at coarse and fine resolutions, using advances coming out of generative machine learning, in particular normalizing flows, we could do what's called domain alignment. So we could align two probability distributions by making an assumption that they're conditionally independent given some latent representation, some distribution over a latent space. And so we would learn flows connecting the two variables that we care about separately to this, this latent space. And then we'd have a posterior over the latent space that, with respect to that conditional independence assumption, allowed us to approximate a joint distribution then for the two variables of interest. So when your two variables are actually the same fields, but at different resolutions, then you've got an upscaler out of this, a downscaler, and in both directions, it's actually generative. So you could condition on a coarse resolution image and output as many samples as you want at a fine resolution, or vice versa. Or you also now have this interesting posterior over this latent space. The latent space itself might not be interpretable, but you could sample from it directly and pass your samples through to get either coarse or fine resolution data. Or you could do these sort of interpretability studies like an interpolation. So here, after the model was trained, we had precipitation maps at the far left and far right. And these are the inputs now, just after the model is trained, and all the other images on the slide were generated. So we map this actually fine resolution precipitation map into a point in the latent space, and then we can sample as many coarse resolution maps as we want. Here are some of them. But then we can also walk through latent space. And then in each point that we walk in, connecting these 2 points, we can generate coarse and fine resolution images, which shows like a visualization of, how the model would interpolate between time of precipitation maps at the particular resolution. Just a disclaimer, it's an active, hot area of ML research. How do you walk over this posterior in your latent space? Since now we've moved away from Gaussians, as I'll mention on the next slide, we've got some weird geodesic path we want to take. This gets into questions that we see in optimization, right? Like how much computation should we take to perfectly follow the path versus doing, linear approximations where we might step off the manifold and have to project back. So it's an interesting area. And kind of the engine behind all of this kind of finishes that story that was started with variational autoencoders, which is this idea of normalizing flows. So with a normalizing flow, while you may have started with a simple, say, Gaussian prior, you can complicate your distribution more and more. Now, of course, if you complicate your distribution, so much that you overfit to your data, that's not great. So you're still going to have some regularizer that's pulling your distribution back closer to the prior that you balance off against in the loss function that you train with. But these distributions are complicated by composing a set of functions, and that's what's called the flow, the composed function. Now they have to be bijections. You're learning their parameters, and there's certain functions that are possible. But what it allows you to do is all kind of your probability math can sort of happen in your original clean space, like your original Gaussian prior or whatever. And then you also have cycle consistency for free because these are all bijections. So the idea about that align flow paper that Brian extended to geospatial data downscaling is that I'm going to learn a flow from my fine resolution data to my latent space, and simultaneously also learn another flow, so this meaning fitting parameters from my coarse resolution data to my latent space. And yeah, I forgot if there was anything else I wanted to say here because I'm trying to not say too much. Okay, so yeah, and on point predictions, we could do better than state of the art, or do about the same as state of the art techniques in the downscaling field. But then we could also create all these generative downscaling distributions that we hadn't seen before. Okay, so I'm now wrapping up and preparing for the discussion. So for the machine learners, they might be interested for the discussion about what kind of new things we did in ML along the way of this big experiment on AI for climate change and environmental sustainability. We did a lot around online learning and brought it to spatiotemporal non-stationarity, which had not been studied, which also included being able to predict at multiple timescales simultaneously and share information about our learning skill at the different timescales. I talked about the avalanche problem, but that could be just a general approach to how do you deal with severe class imbalance with very limited supervision. And then here's a box that really hasn't been checked, which is more of a placeholder for all the scope that there is to take problems that seem to already be treated by computer vision and actually solve them in our domain. So, I mentioned highly deformable patterns like those cyclones, convection or these ephemeral patterns on fluids are much, much more deformable and can even disappear. Whereas a deformable object, as per standard computer vision papers, would be a human, a cat, a car, something that is not going to completely disappear. Also, when we look at spatiotemporal data, different papers are coming out with general pretext tasks or self-supervised learning approaches for spatiotemporal data. But if it's in the computer vision literature, they seem to make some kind of assumptions that you just have video. And video data has, a foreground and a background. It has certain conceptions of depth that when you just have spatiotemporal data fields, cannot always be learned. But we that are wanting to design algorithms do take this as a positive, is that there's research to be done. I have a few summary slides. One of them is along the lines of if we have a lot of data diversity in the spatial dimension, can this help substitute for all that we're going to lack in our time history, right? All this instrumentation has only come on very recently. And so, and there was also no counterfactual past. So there's so many instantiations of Earth that didn't happen. But instead we have more and more and more fine resolution spatial data. So can we somehow substitute the diversity there for the temporal scope that we lack? Interpretability, it's all well and good to use generative models, but how do we then interpret the distributions that they generate and how close they are to reality? If we had a closed form generator for reality, then we wouldn't have even been learning these generative models. And so these sorts of questions are open even in core ML. Although there's been some progress, just checking that your model is not just memorizing the training data. And finally, taking it back to long-term inspirations. I started with the cascading hazards. We needed solutions yesterday. This is a long-term inspiration. And another long-term inspiration is around climate justice. Certainly, if we're deploying AI-driven warning tools for wildfires or cyclones, we don't want to create more inequity, but really, in at least, I'm at this point more familiar with the US, but we have a legacy of climate injustice. It would be great if we could really ground our focus on data-driven tools that would help us undo this legacy. So thank you for the people contributing to the work that I presented. That's my Boulder group. And I'm also building up a France group funded by this Choose France chair by the French government and located at INRIA. So I am recruiting. I mentioned the journal, submit to the journal if you're already in this space. And whether or not you're already in this space, there's a new synthesis center that NSF is supporting, led out of CU, but meant to be a national resource. So they're having an unconference style summit. I believe that's already full. That's happening in May. And then they're going to have hackathons and working groups. And so the idea is, say you're a wildlife ecologist, or you're working on some other environmental data problem, but you would really like to inject machine learning, AI, and data science into your approaches. This is a center in terms of computing resources, the ability to create data cubes, and also these events that bring folks together to drive innovation that will help you to do that. So let me stop so there'll be time for questions.
Thank you so much, Claire. First of all, I invite everyone to mute their microphone and let us give a round of applause to Claire for this very interesting presentation.
Yeah, thank you very much, Claire. Yeah.
Thank you. Now, if any of the attendees wish to ask any questions, please feel free to unmute yourself. Also, you may write questions in the chat and we can read it. Please feel free. I mean, you could ask about the presentation, but also Claire is involved in so many other events and projects. I think that Claire will be open to answer questions outside the presentation.
I can start
Yes.
off if it.
Yes, Arup, thank you.
Yeah.
Claire, thanks for your wonderful presentation. I think you're one of those who come from a very strong machine learning background and then are so deeply steeped into climate and earth sciences. So that's wonderful, and it's always educational for me to attend your talks. So the question that I had for you is not necessarily related to some of the materials you have, but maybe a bit broad. So we are hearing these days about foundation models. So for example, and I just sent a link in the chat window. I'm not sure if you can access that, but that's fine. I mean, this Microsoft came up with this, what they're calling climax model, which they said that they have trained with lots of CMIP, these large Earth system model data. But once they have trained with all of those data sets, they claim that this model can now do various things which those other models cannot. So they have seemed to learn things such as, higher resolution, generating higher resolution outputs, generating outputs at weather scales. I mean, to some extent, we are aware of the debate going on in the machine learning community about, the value of Occam's razor or not, or the unreasonable effectiveness. So from your perspective, for some folks like us who are in environmetrics or coming more from the domain side, if you will, and have tried to go a little bit into the data science machine learning side, what should how should we look at this? Should we start to evaluate these climax kind of models more seriously, just as we do in other Earth system models? Is it too early? I'm just interested in your opinions on these kind of approaches.
Yeah, I'm kind of following along in real time as well. But at this point, I would maybe have 2 points. One is, don't start listening to them as you would an Earth system model, but please do jump in and start evaluating them on what tasks are they good, what are their failure modes, what are the tasks that they're claiming predictability that you can, from a process-driven or data-driven approach, show is not actually even predictable. Because then each of those cases that are raised will be something that anyone developing a foundation model will have to address. I mean, it basically creates specifications. And I mean, even the people publishing these papers, there's also GraphCast from DeepMind. And then, you know, NVIDIA is apparently going to make a digital twin. Each of these, all of these approaches are not claiming to have fully solved it yet. So it is early days. And now with your expertise is the perfect time to jump in and check that if they have any skill on the areas that you have expertise about. The larger point, though, that I want to make, and this is very in parallel with current events that we're seeing around, you know, large language models and deep fakes and et cetera. And, you know, people saying that, oh, AI is so good at being creative, or AI is a better writer than humans, so we can just let AI write all the context. Well, the AI is just a very fancy amalgam of everything humans had already written, or all the art and pictures that humans had already taken. And similarly, we're not ready to throw away the climate and weather models. And in particular, we don't want to throw away the climate and weather modelers or the domain scientists, because this model was only trained up until a point, and any scale it has is because, you know, ERA 5, this reanalysis product, which encodes a lot of physics knowledge, was skillful, and any limitations it has are going to be also due to the data. So if we just throw up our hands and never study like dynamics or processes again, then we'll just be limited at 2023 knowledge, I believe. And yeah, I mean, there's all sorts of existential questions coming up right now with AI. But yeah, thank you. I think also there is a lot of scope for small collaborations of machine learners and domain scientists to play with any of these foundation models, and again, find the failure modes, or because it could also lead to interesting science, I believe. It's not just to make the AI smarter. But yeah, that said, I'm still formulating my thoughts, and thank you for bringing that to the table. And nice to see you. Arup is one of the editors on EDS.
Thank you very much, Claire, very insightful.
Thank you. Yulia, you have a question?
Yeah, thanks very much, Claire. As usual, the talk is fascinating. I have a couple of questions. So one is that there are two recent trends in ML. One is trying to represent spatiotemporal data as graphs. You know, so that also addresses many statistical questions related to non-stationarity and non-separability in space and time. So have you tried those techniques in your studies? That's the first question. And the second one, especially given that you try to address non-stationarity. And the second one is trying to use more physics-informed tools within deep learning.
Sure. I'm not sure if you're referring to like the climate networks kind of approaches, or if you're more saying,
It can be
hey,
climate
okay.
networks, but it doesn't
Yeah.
need to be. It doesn't need to be necessarily climate networks. You can
Right.
have any type of a spatiotemporal data, and essentially you represent it as a graph. It's more related, I would say, to causal representation back in the 90s. Do you remember, like all this graph?
Yeah.
And then you no longer work with Euclidean space. Okay, so I mean, you bring everything into, you know, either graphs of manifolds, yes, and then it's different MEL tools that you can use, because
Yeah. I'm interested where like the graphs are somehow learned from the data. Like Arindam Banerjee a ways back had this really interesting spatial graph that he learned over South America that could learn that there were no edges over the Andes Mountains in terms of similarity. And I believe that was something like you were doing multitask learning, and I guess the prediction in each location was a task, and then you wanted to learn task similarity. So there's a lot of different techniques. When you first mentioned it, I was thinking of spectral techniques, and you know, in other problems we've done spectral clustering. The closest I've come sort of to spectral techniques in climate was actually not spatial, but we did the idea of like a sparse matrix completion to say, hey, all the climate models are just sort of different real possible future realizations, and then we're missing some data, the future. So can we complete it by, you know, taking some assumption that we're on a lower dimensional manifold. So we're, you know, looking for a reconstruction that still has some nice spectral properties. About the physics informed, there are a lot of people doing physics informed, and so far my team has not done physics informed. So if you don't have labeled data, then physics is one form of getting supervision. Our team, I think at this point, is a lot more interested in self-supervision, where you design pretext tasks, you know, hopefully not as silly as the autoencoder, but that's along the idea of it, where in computer vision, people said, if you take an image and then chunk it into chunks and then rearrange them, you don't need outside supervision, but now you can give that as a problem to your learner to rearrange it. And if they learn to do that, then they're learning interesting spatial features. So that's the approach that we have taken. But I do follow the physics-driven literature. I think that's interesting. My philosophical question is, though, that if I'm playing with data that is the output of a physics-driven model, whether it be an actual NWP or GCM, like a completely physics-driven model, or reanalysis data, which was the output of data assimilation, which means that physical laws were used to create the data product, then I don't want to kind of be redundant. I don't want to just learn the physics where the physics was already used almost to generate the data product. So that's my only caveat, but I think it can be a good stand-in and structural thing to lean on, because many of these, most of what we're seeing can easily or can be explained somehow by the physics.
Hey, yeah, thank you very much.
Okay.
Thank you.
Thanks.
We have another question, if we may.
Yeah, I have time. I don't know about everybody else on the
perfect.
call. I feel like I went
Thank
too
you so
long,
much, Claire. We have a question on the chat from Jaydev Goel. How much of an issue is model drift within climate change machine learning? And if it is an issue, what are some ways in which we can make models more robust to drift without continuous investment in model tuning?
Yeah, so first off, that was partly the motivation of that first line of work I did, where we did online learning to adaptively combine the ensemble predictions, because climate models generally do have a nice consensus on what we've seen in the past. Well, why is that? Partly because if you run on data from the past and you're not modeling it well, then you'll change something in your model. So kind of an indirect tuning has taken place. But this drift is that you're running simulations of dynamical systems. Eventually, they're kind of gonna, diverge from initial conditions. And I think that's what he is referring to, he or she is referring to. Yeah, so there's non-stationarity, not just in the observations, but then in these model realizations themselves. And that's why that's one of the, and we address that partly by using online learning. But also, I didn't spend much time on this, but there's sometimes, there are sometimes these seasonal to sub-seasonal prediction products that are reinitialized every month, but then every month they will still then output predictions for every single month in the next 11 months. So in January, you predict February and you predict March all the way up to December. In February, you predict March and all the months up till the next January. So there is some reinitialization that might happen on some of these shorter scales. And we can use machine learning to exploit that as well. But I agree in that, yes, there's no magic in ML. And if the models just are not good after a while, then we can't we can't trust what ML is saying about the model data way into the future. But finally, if you asked any climate modeler, someone who actually works on the climate models, they would tell you, for climate, we want to look at the distributional properties. We want to look at an ensemble of climate models. We want to vary over the input conditions of the models. We even want to test different parameter settings. And so they're doing a lot of things to try to inject some randomness and so then get answers that are averaged over more possible options. And so they also would probably say that when you're looking at average climatological behavior emergent from climate models, you generally are only looking out about 30 years with any fidelity, because the modelers are definitely aware of the drift. And maybe you're actually a modeler, but anyway, thank you for the question.
Thank you, Claire. We have more questions on the chat, so I'm going to read one more from George Milosevic. It is fascinating that anomaly detection with VAE for avalanches would work better than supervised classification, since classification is optimized directly for the task. Thus, everything that is different from the norm result he means larger reconstruction loss in avalanches in your data. Why not attach the classifier on the latent space?
So a couple things. Yeah, this is a good point. Some people say, well, it might not be an avalanche. It could be something else. And for this application, it was literally just images of, the surface of snow with or without the avalanche deposits on it. And so we were fine with one threshold, but it is certainly true that if you have multiple kinds of anomalies, you could do something else as your wrapper. So that wrapper could have, say, multiple thresholds, or you could have some other kind of classification or regression on that. Attaching the classifier to the latent space, I don't 100% know what that is, but that sounds very interesting.
Excellent. Another question that we have from Niti Mishra. May I ask you to please point out the progress you had mentioned early on checking that the ML model is not just memorizing the training data?
Yeah. I will try to give you the exact citation. I think one of the authors is Sanjoy Dasgupta. I believe another author is Kamalika Chowdhury, but I'm definitely Dasgupta is on it. Let me just, okay. It is AI Stats 2020, Meehan, Chowdhury, and Dasgupta, a non-parametric test to detect data copying in generative models. So basically, we're at the point where there's some kind of test. You can test how, like, you can test that your GAN is not doing something really, really bad that's just memorizing the training data. But that is, one step along this whole spectrum of how can we judge the realisticness of this distribution. People are going off and using generative models to make precipitation fields, as I showed you, or make fake clouds. And the domain scientists are wondering how realistic the distributions are. And, this is still quite open in core ML.
I see. Clear. I have one question from my side. I think that would be probably the last question. You mentioned your progress, well, a little bit of the research that you are doing on justice, injustice, on the justice injustice area. Can you please expand a bit what you are working on there, and future prospects, etc.?
Sure. So I think the concrete thing that we've done so far is basically trying to collaborate on projects that are in the Global South, because we know that the Global South has outsized climate change impacts, where the Global North generally did a lot of the burning of fossil fuels that has gotten us into this place. So I'm starting up collaborations in West Africa and had some collaborations in India. But in the US alone, and when I was, writing grant proposals focused on the US, we were just trying to really address this legacy of climate injustice. So there are some communities that were low income, BIPOC, that were getting a lot of incinerators and sewage plants and factories put in them. And that's sort of environmental injustice. And also maybe less trees were being planted and they were less wealthy and well off. And so then there were worse health outcomes in terms of, things like lung disease and et cetera. So we were proposing, although we didn't get funded, but it was a grant proposal. We were proposing that if you're going to have a warning system for like how a wildfire is spreading, you should prioritize, of course, communities in the high probability path, but you should also prioritize communities that are already vulnerable due to, bad pollution in their regions that are even in the lower probability path, because those are more vulnerable. And I'm hearing something. Anyway, yeah, that's one of the ideas that I meant. And it'll be interesting, in Europe to see sort of what the issues are here around environmental justice.
Have you tried to link it with governance or policymakers or something around that? I mean, that will help to sell the idea, at least for a grant proposal,
Yeah, so I have contributed. So I co-authored a white paper called Computing Research for the Climate Crisis that was from the Computing Community Consortium and generally gets an audience at NSF. And we wrote about environmental justice as one of the key threats of climate change, because if anything, climate change is just going to make more inequity in terms of air quality, water quality, what poverty deprives you of is going to be like healthy living conditions. And actually, then we also workshopped it, and recently a convergence accelerator topic was announced on water and water justice. Luckily, the current administration in the US has a whole panel or committee on climate justice. So it's a good time to try to submit projects on that. And actually, there's a new call called NSF Crises out of NSF that's specifically looking at like the societal impacts of climate change. And then I've, try to affect policy on the NSF Advisory Committee for Environmental Research and Education. And we do keep framing climate change as a justice issue. So that might be the policy here again is like what kind of program announcements there are for grant funding. But then I'm also part of something called GPAI, which is the Global Partnership on AI, had a committee on climate change and biodiversity, where they can help advise governments. But again, it's really more about, if we want to address climate change, we can speed things up a lot by using machine learning. And so advising governments on how to incorporate that safely. Mostly, I didn't do a lot around policy yet, because at least in the US academic system, a lot of time is spent on like getting your tenures and promotions. And I didn't stick my neck out politically much yet. And there's also a host of other political issues wherever you go. Right now I'm in France and there's strikes like every week with their own political issues. So anyway, I haven't started. I don't know. Do you guys work on the governance aspect at all? That's interesting to me, but not something that I've worked on much. Is that part of like what the TIES community does?
Well, we are trying to do something, but I can't say that we have anything on the sort.
That's great.
But I just put in the chat that we are organizing workshop on environmental justice, and particularly in conjunction with health outcomes at the next ICHCAI conference. It's going to be in August in Macau.
Great.
Thank you, Claire. Thank you so much for answering all our questions. I mean, and giving us more than we expected from your time. For now, we are going to stop the recording, but we can continue the discussions without being recorded. Please remember to visit our website to keep you updated on the next speakers and events.